Hi everybody, another practice problem video by physacademy.com. In this video, we will work through a two-dimensional momentum practice problem. Let's read the problem statement together and step-by-step analyze it. An evildoer has stolen an unstable atomic nuclear object with a mass of 17 times 10 to the power of negative 27 kilograms from the unstable nuclear mass facility. While waiting at a stoplight, the unthinkable happens. Actually quite expected and predictable up to a probability. And the mass disintegrates into three particles. One of the particles, of mass 5 times 10 to the power of negative 27 kilograms, moves along the positive direction of the y-axis with a speed of 6 times 10 to the power of 6 meters per second. Another particle, of mass 8.4 times 10 to the power of negative 27 kilograms, moves along the positive direction of the x-axis with a speed of 4 times 10 to the power of 6 meters per second. Find the magnitude and direction of the velocity of the third particle with respect to the negative direction of the x-axis. Alright, when I see a problem statement about a sudden change in the system state, I consider two possible approaches. One is the conservation of energy, and the other is the conservation of momentum. Sometimes we need to use both of these methods, and sometimes, one is enough. In this case, we don't know what chemical reaction happened to quantify the system's stored energy before the explosion, so our only option is the conservation of momentum. Now that we know the conservation of momentum is our option, as the momentum of an object is a vector, we need to start sketching a coordinate system. At first, before the explosion, the initial object is right at the center of the coordinate system and at rest, meaning it doesn't move. Later, after the explosion, it breaks apart into three pieces. One moves along the positive direction of the y-axis, the other one moves along the positive direction of the x-axis, third and the last piece, well, we are about to find out in what direction it is going to move. But so far, by just analyzing the system, we can say it will be toward the bottom left as its momentum needs to cancel out the two other pieces' momentum. Let me rewrite all the given variables, their corresponding values, and what we are asked to find here again so we don't need to go back and forth to the problem statement. As usual, when we deal with a two-dimensional problem, I work through it in two columns in parallel. One for the variables along the x-axis and the other for the y-axis. The conservation of momentum means the sum of the momentum of all of the involved particles is the same as the sum of all the momentum of objects later. Here, one object breaks into three pieces, therefore, on the left-hand side of the equation, we have only one momentum, and on the right-hand side, we have three momentums, one for each piece. Again, since momentum is a vector, we need to break our calculation apart into the momentum along the x-axis and then momentum along the y-axis. To calculate the momentum of an object in a particular moment, we multiply its mass by its velocity at that moment. Along the x-axis, we use the x component of the velocities, and along the y-axis, we use the y component of the velocities. Here, in particular, we are calculating the components of the velocity of the third object, meaning v3x and y, highlighted in yellow. Analyzing the other variables, we see that other than the mass of the third object, everything else is given. Since we already know the total net mass and the masses of objects 1 and 2, we can calculate the mass of the third piece by following these steps. Now that we have the mass of the third piece, let's go back to the equation and mark off the variables that are equal to 0. For example, we know the original object was at rest, therefore its velocity both along x and y are 0. Or, we know that object 1 is moving along the y-axis, so its velocity along the x-axis is 0. And the same for object 2, its velocity is along the x-axis, so its y component is 0. Okay, let's rearrange these two equations and keep the x and y components of the velocity of the third object on the left-hand side and everything else that we already have a value for them on the right-hand side of the equation. Before plugging the numerical values in, let me really quick check the units to make sure I'm not missing anything. As you see, the final unit of the right-hand side is the same as the left-hand side, and it is in meters per second, the SI unit of a velocity. Now let's plug in the values and find numerical values for the components of velocity of the third piece. Since we are asked to find the magnitude and direction of the velocity of the third piece, I'm not going to right away put the values in a calculator and round up the number. If we start rounding up the numbers too early into the calculation, the little margins of errors can get multiplied and get larger as we continue further into the numerical calculation. Anyway, here, we can factor out a few of the variables that are marked in green. Alright, this is the velocity of the third part as a vector in meters per second. Now let's calculate its magnitude and direction with respect to the negative direction of the x-axis. Now that we are at the very last step of the numerical calculation process, we can go ahead and, using a calculator, find the final value of the magnitude of the velocity, which is 12.512 times 10 to the power of 6 meters per second. And the very last part is the direction with respect to the negative direction of the x-axis. And the final angle is 41.8 degrees. Remember, most calculators, by default, give the angles in radians, and you need to convert them to degrees yourself or change the setting of your calculator. Thank you very much for watching this video. Please check our website, physacademy.com, or our YouTube channel for more practice problems. If you found it helpful, please consider subscribing to our channel. This is the best way to support our work, and have a good one.